So now let's discuss about this stability. One question regarding what we were discussing before. So stability of carbocation. We need to calculate the order of stability of carbocation. So NH2 and one positive charge here, and CH2, 3H3 and CH3 here, and we will compare this with CH3, CH3, and here positive charge, and the last is, well, both are methyl group. So we need to compare the stability of these molecules. So as we have studied before, this NH3 will donate the because this carbon has the positive carbon has MTP orbital, so this will donate directly from plus M, and this will donate from plus H because of the alpha hydrogen alpha carbon, and plus I also. It is also donate from plus H and plus I. And here in this example, this is B, this is C, this is first. So in B, this is resonance because of the double bond, so the conjugation will go from here to this positive thing. This is plus R effect, and these are plus H and plus H. And in this molecule only plus H and plus H are present. So as we know, the mesomeric effect is more, so plus M is more as compared to plus R and plus H and plus I. So the order of stability will be A, then B, then C. This will be the final order for this question. So there are some rules to determine the miscellaneous question in which the GOC or general organic chemistry gives the different answer, and here are the rules, or it is an observation based rule, so according to which, if this type of resonating structure is present, then we count the alpha hydrogen value here is 6 alpha hydrogen are present here, and if a nitrogen is attached in a ring or anything, then we count this as 12 alpha hydrogen, and if an oxygen is present, then we count it as 8 alpha hydrogen, and then fluorine is present, then we count this as 4 alpha hydrogens. So this is an alpha hydrogen as basis of this rule, observation rule. So let's take an example of this. So if the CH3 is present here, and a methyl group is here, and a methyl group is here, and a methyl group is here, then, and if this type of group is present with a positive charge, and a CH2 with positive charge, and a fluorine is attached here. So as we know, if we put a general organic chemistry here, so the order will be, this chlorine is donating here according to plus M, and this is plus R, and this is plus H. So according to GOC, the order will be the mesomeric will be first, so the C will be first, then B, and then A. But this is a wrong answer, but because of this observation rule, so the final alpha hydrogen that we count here is 1, just like here methyl means C, and 3 hydrogens are present. So number of alpha hydrogen is 1 2 3 here, 1 2 3 here, and 1 2 3 here. So 9 alpha hydrogen are present here. And in this molecule, as we discussed here, the alpha hydrogen count is 6 alpha hydrogen, and in this molecule a fluorine is attached, so the alpha hydrogen here will be 4 alpha hydrogen. So the stability order is directly proportional to the number of alpha hydrogen present. Stability of carbocation is directly proportional to the number of alpha hydrogen present, so it will be A, then B, then C. this will be the final result, this will be the wrong result. So there are some examples in which by putting general organic chemistry and by this rule we get the same result, so this will be beneficial. But in some cases when we get the after applying GOC, when we get different result as compared to applying the alpha hydrogen rule or the observation rule that we discussed here, so we prefer observation rule more, we prefer more as compared to general organic chemistry. So this will be the final answer and right answer. So here is an example of stability of carbocation. So as you can see here, we have an aromatic compound. Here we have aromatic compound. So the stability of this aromatic compound compared to this phenyl ring, because of the aromaticity, this will be more stable as compared to plus R or the pH ring which apply plus R here. And here two rings are applying plus R and one is plus H. So this will be more preferred as compared to more R group are present here. Here two group are present is compared to this and this will be more stable, and here this will be more stable because one phenyl, here two phenyl group present, so plus R, and here plus H and plus H, so this will be more preferred. And in this comparison here also one phenyl ring is present and one hydrogen is present, so it is not doing anything, and this is plus H, so here 2 plus H is present, so this is also more stable as compared to this. After that, if we check this molecule, it has plus H and plus H, so it will be stabilized as compared to, because phenyl ring plus R is present here, so this will be here also plus R, so here it is also this is not stable as compared to this. After that, if we check again, then this will be the final order of these groups. So now let's discuss about this last two example. Here we see a concept according to which we know that this is a phenyl ring, so this carbon positive and a phenyl ring is present here. So what happened here is, this is a example of resonance. So due to conjugation, here conjugation is present between these molecules, so this will be more stable as compared to single double bond because no conjugation is present here. So conjugation के कारण this is more stable as compared to this ring. And if we count alpha hydrogens, so that is also getting more alpha hydrogen. So we don't count alpha. So here are some examples for the stability of carbocation. Let's check this example first. So according to this example, here one NH2 group is attached, so let's count the alpha hydrogen here. So according to an NH2 group, nitrogen is present, so according to that rule that we observed, 12 alpha hydrogen are present for nitrogen, so 12 from here and 3 from here and 3 from here, so total 18 alpha hydrogens is present here. And in this oxygen we count this as 8 alpha hydrogen, and this carbon has 3 alpha hydrogens, this methyl group has 3 alpha hydrogens. So if we compare this order, these three molecules order, so this will be the final stability order of carbocation. And this phenyl ring, this will be the number of phenyl ring is more, so more resonance will be applied and more stable will be the ring. In this example, the stability of carbocation is, the stability is increased in linear conjugation, not in cross conjugation, because this electron density can go here also, so it is not only available for here, but here all the groups are coming in one direction and fulfilling this electrode, this positive charge. And this is in cross conjugation, so linear conjugation is good for stability. In this example, stability of carbocation, one CH3 group is present here, and this is plus charge carbocation, so this is plus H, so plus H will be more favorable. And we know that in ortho position and in this ortho position, plus H and plus R can be applied, but in this position, meta position, only inductive is seen, only inductive. So plus I group, plus I effect is applied here. And in ortho and meta position, plus H group is available. So the stability order will be more for this plus H and plus 3. Plus H can be more dominating, so 1 is more favorable. Both have plus H effect. Now after checking plus H, let's check about the plus I effect. So plus I effect is distance dependent effect, so this will be more favored as compared to this long distance. So first, then third, because of the hyperconjugation, and the last will be inductive effect of CH3, donation of inductive effect. So this will be the order, this will be the final order. Now let's check about this question. So in this group, in carbocation, NO2 group is present, so it is an electron withdrawing group, and it's present in meta position. So here only inductive is applicable, as we have seen. So the ONO2 and OCH3, who will be the most who will be taking more electron from the, who will be more unstable. So this is more strong electron withdrawing group, compared to NO2. So the order will be, this is for the plus I, so 3 will be more stable because it is donating, and carbocation is required of donation because this is donating, so it will be good. So plus I with, so third will be more stable. And who will be more after that, third, then first, and then B. So here it is also a very important example, as you can see here. So in case of this ring structure, let's check this example first. So in case of this ring structure, if a positive charge or any charge is present, so only inductive effect has been seen, other effect can be neutralized. So the inductive effect is distance dependent, so this will be more favorable or more stable. So second, then first, then first, and then third. This will be the final order. And the next question that we can discuss here, so let's check this question out. So here, as you can see, and C carbon with 3-methyl group is present, and as you can see in the meta position, only inductive effect has been seen, and mesomeric cannot be applied here. Why? Because no alpha hydrogen is present, so inductive effect can be seen, only inductive effect can be seen. So as we can see, inductive effect is a distance dependent effect, and due to increase in mass of deuterium as compared to hydrogen in the isotope, so bond cleavage can be more seen in CD3 molecule. So this will be the final stability order in which donation is possible. Now let's discuss some more concept. Now in this example, as you can see here, more bulkiness, if a group has more bulkiness, then the hyperconjugation, which is, or the resonance, or anything, any group, due to presence of more bulkiness, the chances of getting the plus H effect is reduced. Why? Because of these, this concept is called SIR, which is steric inhibition in resonance, according to which, as we can see, the resonating structure has the same electron density or the same plane present in all direction. So the electron density can travel through this CH2 from all these rings. So this is the resonance structure, but due to presence of external groups, due to presence of some hindered or some bigger groups present, this plane, this bond, this MTP orbital present in carbocation is getting out of the plane. So this will get out of the plane, and due to presence of this hinderedness, so this will become a little tilted, and resonating structure, or it will decrease the stability of this molecule. So more the number of charges are present in this type of molecule, so less will be the stability. So the stability order of these molecules, second, third and fourth, will be 2, then first, second, third and fourth, not the other way around. Now let's check another concept, which is the concept of dancing resonance. So what is a dancing resonance? So it is a type of resonance which occur when a three-membered ring is cut and a carbocation is present in this position. So it will break the bond, and double bond is present, and a positive charge will go here, and it can be formed in this direction, and it can be formed in this direction. So the number of three-membered ring, the more the number of three-membered ring, more will be the dancing resonance, and dancing resonance increases, which increase the stability. The stability also increases. So the final order will be this. Now let's discuss one example from the bridgehead carbon. So these are the two molecules. We need to calculate the stability of these molecules. So as we can see, one positive carbocation is present here. So the number of alpha hydrogen here is 1, and 3 from here. 3 alpha hydrogen is present, and 1 hydrogen is here, but we cannot count this because it is in the bridgehead carbon. And if we take this hydrogen, then this double bond will be very unstable, so we cannot count this hydrogen in this type of structure. So their number of alpha hydrogen is 3 from here and 2 from this direction. So 5 alpha hydrogen can be present here. And in this molecule, if a carbocation is present here, then and a carbon with 1 hydrogen and this 2 hydrogen, so number of alpha hydrogen here is 3. So the stability, as according to numbering, this will be the final order as the stability. Let's take another example. Here, as you can see in this diagram, if here is a carbocation, so the alpha hydrogen is CH3 from here, 3 from here and 1 from here. So number of alpha hydrogen is 6 and 1 7. So there are total 7 alpha hydrogen present in this ring. And in this case, if a carbocation is present in this position, then here no alpha hydrogen is present, only 2 alpha hydrogen is present. So here 2 alpha hydrogen is present. We cannot count this alpha hydrogen because of the same reason. So this will be the order of stability. And in this example, example 15, the stability, the ring size is here 1. Now let's discuss this. As the number of this bridgehead carbon is increasing, it will become more planar. So the planarity increases as the number of this carbon increases. So 180-degree angle can be easily reached because of the strain reducing capability of this. So the stability order can be: C is more stable, then B, then A. Now let's discuss about the stability of carboanion. Anion means negative charge. So negative charge is present here. So if a ring is present, then this negative charge will take this, and this will form this resonating structure. These are the resonating structure for carboanion. So negative charge can only be occur at ortho and para position. So same can be applied for in the previous, as we can see, only inductive effect can be applied in meta position. As we can clearly see from the example, the stability of carbocation is directly proportional to minus I effect and minus I effect and minus R effect, and inversely proportional to the plus R and plus I effect. The stability of carboanion. So these are some examples of stability. So in this example, in carboanion, there is donation from plus H, and here a donation from plus H is present, but both the donation are same. So let's check the inductive effect. So after checking the inductive effect,